So what if I told you there's a way to make your C programs run, like, way faster, without even touching the main logic? Well, today, we're going to pull back the curtain on a super powerful technique that lets you do just that.
Okay, check this out. On the screen, we've got two programs. They're doing the exact same heavy lifting. But look at the runtimes. The first one clocks in at around 4.5 seconds. The second one, whoa, just 2.5 seconds. I mean, that is almost twice as fast.
So that's the big question, right? How is that even possible? It's the same task. What's the secret sauce here? What's that magic trick that just sliced the runtime nearly in half? Let's figure it out.
And the secret, well, it's all about something called threads. This is the key. Threads are what let us unlock this parallel power inside our programs, letting them do more than just one thing at a time.
So what's the difference, really? A normal single-threaded program is pretty simple. It's just one list of instructions that runs from top to bottom. That's it. But a multi-threaded program? Now we're talking. It can have multiple of these instruction lists, all running within the same time frame. It's kind of like upgrading from a sleepy one-lane country road to a massive, multi-lane superhighway.
Okay, so we've got these multiple lanes of traffic, these multiple instruction streams. But how does the computer actually handle that? How does it run them? Turns out there are two main ways this all goes down. Something called parallel execution and something called concurrent execution. Let's start with parallel execution. Now, this is the dream scenario. If your computer has a multi-core processor, which most do these days, it can literally run code from different threads at the exact same time, like simultaneously. This is true, honest-to-goodness multitasking.
But what if you've only got one CPU core to work with? Well, that's where concurrency comes into play. The CPU is so incredibly fast that it can work on a little bit of thread 1, then jump over to thread 2, then back to thread 1. It switches back and forth so fast that it looks like they're all running at once, even though technically only one thing is happening at any given nanosecond. It's a very convincing illusion.
But here's the bottom line. Whether it's true parallelism or that super fast concurrent switching, the goal is exactly the same: performance. We're doing all this, we're adding this complexity for one reason: to make our programs run faster.
All right, that's enough theory. Let's get our hands dirty. How do we actually write this stuff in C? Well, the go-to tool for this is a library called pthreads. That's P-T-H-R-E-A-D-S, and it stands for POSIX threads. Let's walk through the basic steps.
The basic process is actually pretty straightforward. First, you've got to include the header file. Then, you create a special pthread_t variable. Think of it like an ID card for your new thread. Next, you use the pthread_create function to actually launch a function in that new thread. And finally, you use pthread_join to tell your main program to, wait for that thread to finish up.
Okay, let's zoom in on that pthread_create function, because it's really the star of the show. The first thing you give it is a pointer to that thread ID variable we just talked about. The second part is for some fancy attributes, but for now, we're just going to ignore that and pass in null. The third argument is the big one. It's the name of the function you want this new thread to run. And that last one, that's how you pass data into that function.
And that last part immediately brings up a super important question, right? If our thread is off running its own separate function, how do we get information to it? Like, how do we pass it a number or some data to actually work on?
Well, the solution is a classic C trick: pointers, but with a little twist. See, the pthread_create function has to be super flexible. It needs to be able to handle any type of data you might want to throw at it. So what we do is we take a pointer to our data and we cast it to this generic pointer to whatever type, which is called a void star.
This little diagram here shows the whole dance. So step 1, you've got your value. Let's say it's a long. Then, in your thread_create call, you grab its memory address and wrap it in that void star cast. Okay, now, inside the function that the thread is running, it receives that as a void star argument. And then, the final step, to actually use the number, you have to cast it back to a long pointer and then dereference it. It feels a little weird at first, but it's an incredibly powerful trick.
Okay, so now that we've got the mechanics down, let's go all the way back to the beginning, back to that performance puzzle. We actually have all the tools we need now to understand exactly what was going on.
So remember our starting point, our baseline? Two big computations, running one after the other in a regular old program, and it took a solid 4.5 seconds every time. And then, here's the payoff. We put each of those jobs into its own thread, kicks them off at the same time, and boom, the runtime drops all the way to 2.5 seconds. That's what it looks like when you get your code running in parallel.
But, and this is a huge but, there is a very, very easy mistake to make. A tiny change in your code that can completely wipe out all of those performance gains. One little slip up, and you're right back where you started.
Take a close look at the code on this slide. The right way, the fast way, is on the left. You see how we call pthread_create for both threads first. We launch them both. Then, after they're both running, we call pthread_join to wait for them. Now look at the wrong way. We create a thread and then immediately join it. Then we create the second one and join it. The code looks almost the same, but trust me, the performance difference is massive.
And here's the reason why. The whole point of pthread join is to make your main program stop and wait for a thread to finish its work. So if you create a thread and then immediately call join, you're basically saying, hey, start this job, and now I'm going to sit here and do absolutely nothing until it's done. You completely kill any chance for parallelism. You've just turned it back into a slow, single-threaded program.
So there you have it, the incredible power of threads, and the #1 pitfall to watch out for. It really opens up a lot of possibilities. And I guess the real question to leave you with is, now that you know how to do this, what kind of huge, complex problems could you solve way, way faster?